Hey guys, welcome back. So we're still going to be talking about acids and bases. That's what this lecture is about. And here's our agenda for this lecture. So we're going to talk about section 4.3, which is actually a review from 110. We talked about definitions for acids and bases in 110. So I'll remind you of all of that information. We'll then remind you of what it means to be an Arrhenius acid or base, a Bronsted-Lowry acid or base, the acid-base properties of water. We'll talk about the autoionization of water. We'll talk about pH, which is a measure of acidity, and then the strengths of acids and bases. So those are the topics we're going to be covering. All right, let's get started. So an acid-base review. Our first definitions. An acid has a sour taste. It can change the colors of plant dyes. It can react with some metals to make hydrogen gas. It can react with carbonates and bicarbonates to make carbon dioxide. And it does conduct electricity, and that's because it's ionized when it dissolves. Bases have bitter tastes, and they feel slippery. They feel like soap, and that's because soap originally was made out of lye. Lye, sodium hydroxide. They do change the colors of plant dyes. Awesome. And the aqueous-based solutions do conduct electricity, again, because when they dissolve, they're completely dissociated and therefore can conduct electricity with those ions. The first way that we talk about acids and bases is through a definition called Arrhenius. Okay, so there's this guy, his name was Arrhenius. And you kind of sort of need to know this. He said that an acid is a proton donor. And then a base is an OH minus donor. Which, when we talk about lots of things, makes sense. Okay, so HNO3 donates a proton. That's how it is defined as an acid. NaOH donates an OH group, so that's how it's defined as a base. Okay, awesome, we got that. Is that the only way that happens? No, because if we talk about it that way, then we can't talk about NH3 being a base. Okay, NH3 is also a base, so we have to have a more expanded definition. And the first one that we got is from these guys, Bronsted and Lowry. So Bronsted-Lowry acids and bases. The acid definition doesn't change. We still have H plus donors. But the bases do change. And instead of being OH minus donors, they become H plus acceptors. Okay, so you would need to understand what the difference is there to be able to talk about that. Okay. We know that some of the other things that we talked about previously, neutralization. So neutralization refers to a situation where we have just as much OH minus as H plus. So since I have equal amounts of acid and base, that is neutral. That means that the only thing that affects the pH is the autoionization of water. We'll get back to that. And so that pH is 7. Okay, and again, we'll come back to that. It's a complete reaction of equal moles of acid and base. All right. So the number of moles required is dependent on the acid-base stoichiometry. So remember that is necessary when we talk about this. Stoichiometry is a part of what we need to do. We can have formation of gases. I said carbonates and bicarbonates, sulfates and sulfides react with acids to form salts that decompose to produce gases. An example of this is the Na2CO3 plus 2HCl, giving me 2 NaCl plus H2CO3. That H2CO3 spontaneously decomposes to give me H2O and CO2. Okay, so that's one of those processes. Typically, this is a two-step process, just like what we're talking about here. So we form a product, and that product then spontaneously decomposes. Okay? So that's what we're talking about in terms of acid-base review. Awesome. We reviewed what we did in 110. We can do this. Now there's going to be new stuff, right? So we talked about Arrhenius. We talked about Bronsted-Lowry. We're also going to have to talk about another type of bases, acids and bases, and that's called Lewis. Okay, so there was a guy named Lewis, and he had Lewis acids and bases. All right, Lewis acids and bases are something that we're going to define in just a couple slides. So I'm not going to talk about it too much here. Other terms that you need to know about, and I'm going to give myself a little bit of space. We're going to have amphoteric. Amphoteric. The term amphoteric implies that it can act as both an acid and a base. So water is amphoteric because it can act as an acid donating a proton, or it can act as a base by accepting a proton. We need to be able to talk about a conjugate. Okay, this is a term we're going to talk about in a little bit, so we'll talk about that and what exactly that means. We need to be able to talk about binary acids, because you may see this term. A binary acid is something like HCl or HBr. And it's called binary because it has two components. So there's that proton that we can donate and the anion that's left behind. Okay, we'll talk about the definition of oxyacids and carboxylic acid. Okay, we're just going to talk about what those definitions are. I'm not going to worry about it too much. There may be a question on the final about this, but your text doesn't really cover this, so it's something we talk about historically from the text that we used to use. Okay, so those are things that we're going to be talking about as we walk through this. Now, let's get back to our acid-base types. So arrhenous, when dissolved in water, an acid donates H+, and therefore increases the H3O+. So we donate that H+, it gets attached to an H2O, that becomes H3O+, and therefore we increase the concentration of the H3O+. A base, when dissolved in water, produces OH-. That OH- plus an H2O or an H3O+ can give me an H2O back. Can find an H+ that's in solution and can give me an H2O. Okay. Since it's there, that means I'm going to have less H3O+, so it raises the pH. Less H3O+, raises the pH. We'll get back to the definitions of those. Bronsted-Lowry, again, we talked about this. I usually refer to this as BL because I don't want to have to write the whole thing. The acid is an H+ donor. The base is an H+ acceptor. The other thing we need to talk about is Lewis acids and bases. And we don't deal with this too much here. This is something that you talk about in other chemistry classes, but it is a definition and therefore something we should be able to do. In a Lewis situation, an acid is defined as an electron pair acceptor. And the base is defined as an electron pair donor. Okay. Now, all the Bronsted-Lowry acids are also Lewis acids. All Bronsted-Lowry bases are also Lewis bases. Some materials that are Lewis acids are not Bronsted-Lowry acids, and some materials that are Lewis bases are not Bronsted-Lowry bases. So you should be able to look at a particular acid or base and say what kind of acid it is, or what kind of base it is, what gives it those properties. Now, let's talk for a second about what we mean by electron pair acceptor and electron pair donor. And this is always easier for me to start with the definition of the donor, the base. So one of the bases that we talk about is NH3. So NH3. Nitrogen being in that column that he's in, so column 15, 5A, he's number 7. He has 5 valence electrons. 5 valence electrons. Each of the hydrogens has 1 valence electron because he's number 1, so he only has the 1. But there are 3 of them, so that's a total of 3 electrons that are donated. It gives us a total of 8 electrons that we would need to distribute around this molecule. If I were to draw N in the middle, which I do because he's written first, H, H, and H, and it doesn't matter where I draw them. I have to have them all around, and everybody has to have at least one bond. So I draw this bond. And that bond, each one of those bonds contains 2 electrons. That means that I've used 2, 4, 6 electrons in making those 3 bonds. So I subtract that 6, and that leaves me with 2 electrons left. Now, normally, the next step that we would take in making the Lewis structure is to fulfill the octets on the exterior atoms, so anything that's not the central atom. Hydrogen, however, does not need an octet. It needs a duet, and that's because he's in that first row, so he only needs 2 electrons to be completely happy. He currently has access to 2 electrons, right? Because there are 2 in this bond that he can talk to. So he's completely happy. We're not going to need to do anything for that hydrogen. And that means those 2 electrons that are left are put as a lone pair on the nitrogen. That lone pair is not bound to anything. So it can be donated. Okay, and that's what we mean by an electron pair donor. So this empty, non-bonded electron pair can be donated to something else. Right? Now, what is something that might need an electron pair? Well, let's draw the Lewis structure of BF3. So boron, being where he is, he's number 5. His second row contains 3 electrons. Okay, so he has 3 valence electrons. Each F has 7 for a total of 21. That gives me 24 that I need to distribute. All right, we put the boron in the middle. We have a fluorine here, and a fluorine here, and I have 3 bonds, 2, 4, 6. That takes out my 6, and that gives me 18 left if I'm not mistaken. Yes. Okay, 18 left. I need to fulfill the octets on the fluorines. So 1, 2, 3, 4, 5, 6. 6 lone pair electrons plus the 2 that are in this bond give him a total of 8 electrons he has access to. We'll do that for each of those fluorines. So 2, 4, 6 on each one. 6 times 3 is 18. That leaves me with nothing left. So all of my electrons have been distributed. Look at boron. Does boron have an octet? No, he does not. He only has access to the 6 electrons. So the 2 in the bond on the right-hand side, the 2 in the bond on the right-hand side, the 2 in the bond on the left-hand side, and the 2 in the bond below. Okay, so that's 6. He has an incomplete octet. And there's nothing I can do about that because boron, being in the second row, does not have an empty p orbital that he could use to make an additional bond. Okay, he can't. There's nowhere for him to put it. So we can't pull one of these lone pairs like we do sometimes into that to make a multiple bond. Boron can't do it. Okay, so we now have a situation where we have this one thing that has this lone pair that it could donate, and this one thing that's missing a lone pair. So these two can associate. And what I'm actually going to do is I'm going to get rid of that and move this hydrogen up here, which I should have done before. Right there. I have not changed the structure, I just rearranged it. And this lone pair can be donated to that boron. So we've now created a bond between the two. That bond is what we call a polar covalent bond because all of those electrons came from one source. So it doesn't really matter what we call that. That's just so for your information. But that means that we've donated both of those electrons from the nitrogen to the boron. They're still sharing them, so everybody has an octet and everybody's good. Okay? Nitrogen is actually really chemically active because of that lone pair. It can donate it. It can pick up stuff. So that makes him really active. Right? So that's what we're talking about in terms of Lewis acids and bases. So the Lewis acids need a pair of electrons to be donated to them. Lewis bases have a pair of electrons that they can donate. So that's what we mean by that. All right? I told you you wouldn't need much in terms of the Lewis structures, and this is really the only place. And the only reason that I drew them was to show you how those electrons are arranged so that you can see how that works. Do you need to draw them? No, you don't. Now that you know how that works, you don't need to draw them again. Okay? So hopefully that's a little better. All right. Now, that's a lot of information, and you'll see that there's stuff written all over the place and yada, yada, yada. I want you to be able to understand that an arsenous acid is an acid. Okay? It's an H plus donor. The H plus concentration increases. The OH minus concentration decreases. And it's not necessarily another type by definition. Okay? For Bronsted-Lowry acid, it's an H plus donor. It increases the H plus. It decreases the OH minus. It's not necessarily, those are in the wrong order. Oops. Sorry, I said that on the slide before. That's so bizarre. Okay, so that's what we're looking at there. All right. That's our definitions. That's what we need to know. Is it important that you know that by definition, this thing is the same, that they're the same type of, that they're both? Not really. You just need to know what they are. And so if I were to ask you what one of these was, I want you to be able to answer the question, does it fit this? Does it fit this? Okay. So that's one of the things that we'll talk about. The H plus and the OH minus, we will get back to. This is probably familiar to you, but we will get back to that in just a few minutes. But I want to make sure that this is pointed out to you on this slide so that we have everything in one place. So that's what this is for. Okay. We talked about Lewis acids. This is just the drawing that I just did. So here's an actual slide of it. Oops, sorry, I didn't get to the slide. One of the things that you will probably need to do is to be able to look at a table like this and say, okay, what are we talking about here? Now, the strong and the weak, I'm not going to talk about right yet. We will talk about that later on today. But this is the kind of question that you may be asked to look at. So you're given a molecule. Is it an Arrhenius acid or base? Is it a Bronsted-Lowry acid or base? Is it a Lewis acid or base? So if it has an H at the front, then it's probably an Arrhenius and a Bronsted-Lowry acid. Okay. So I could mark this here. I could mark this here. I know that we're then going to have an increase in the concentration of H plus because he's an acid. Is he a Lewis acid? I.e., can he accept a lone pair from another species? And the answer is no. Because fluorine in that bond has access to 8 electrons, there's no space for him to do that. So the answer is no, he's not a Lewis acid base. Okay, so we would leave those blank. We're going to talk about the strong and weak later, but this is the kind of thing that I want you to be able to do. Now, I'm going to leave this question for now. And what I'm going to do is go through this and post these answers to D2L because it's really important that you be able to understand what we're talking about here. So I'm going to do that in the recording after the fact, but I want to make sure that we get everything that might be included on that into one table. So I don't want to talk about all of it right now. Because it says if you're given a 0.1 molar solution of each, and we haven't talked about that part yet. So we'll come back to that, I promise. Questions, comments, problems at this point. Okay, so I'm going to stop here, and I'm going to stop this recording, and I will be back in just a moment to finish out this part. Okay, see ya.